Hi, my name is Michał Drzezinski, and I'll be telling you about optimal embedding dimension for sparse subspace embeddings. This is joint work with Szabaris Csenakot, Xiaoyu Dong, and Mark Rudelson, and we're all at the University of Michigan. So at a very high level, what we're going to be talking about is low dimensional embeddings. So the classical version of this task is that we have a large number of high dimensional vectors, and we would like to construct an embedding. So basically a mapping from that will map these high dimensional vectors to some lower dimension, let's say some lower dimension M, so that the pairwise distances between the vectors in Euclidean distance sense are preserved up to some multiplicative factor, let's say 1 plus minus epsilon. So for example, here we have 3 points. We want to embed them into a one-dimensional space with this sort of mapping, so that the relative distances are approximately preserved. Okay, so a classical result in this area is the so-called Johnson-Lindenstrauss lemma, which essentially says that these embeddings exist, and we can reduce the dimensionality of the high dimensional vectors drastically with a very simple kind of randomized scheme. So here the scheme is basically we take a Gaussian matrix, right, which is an M by N matrix, which defines a linear embedding, right, which has IID Gaussian entries, and we apply that. So that's our embedding. We apply that to each of the high dimensional vectors, and it turns out, it can be shown that this embedding will, for any set of points of size, let's say capital N, we can, this random embedding will, with high probability, successfully, reduce their dimensional or preserving the pairwise distances down to the lower dimension of log n over epsilon squared, right? So to the logarithm of the size of the point set. And this is something we can call, or we're going to call, an epsilon delta embedding, meaning that the random embedding preserves the distances up to multiplicative 1 plus epsilon with probability 1 minus delta, right? Now, the remarkable thing about this is that the embedding F, the random embedding, is oblivious to the choice of the point set D, right? So the way we constructed the randomized embedding was entirely independent of the point set, right? And yet it will work for any such point set with a very high probability, right? So that's called an oblivious embedding, right? Okay, so now the dimensionality reduction obtained here was quite striking. We went from n points to log n dimensions, right? But what if the point set D is infinite? So obviously then the previous statement is vacuous, right? But there might be settings, very natural settings, where we would expect to be able to achieve dimensionality reduction from an infinite point set. And kind of the most obvious example of this is a d-dimensional subspace embedded in a high dimensional space, right? So clearly, if the point set already lives in a d-dimensional subspace, then there is a low dimensional embedding to that d-dimensional subspace. But you can further ask, is there an oblivious embedding that works for all d-dimensional subspace, kind of by the analogy to the oblivious embedding for the finite point sets? So here's how we would define this. So this is, we're going to call this an epsilon delta D oblivious subspace embedding. So F will be such an embedding if it is an epsilon delta embedding for every d-dimensional subspace in some Engian dimension Rn, right? So that means for any d-dimensional subspace, this function, which is allowed to be random and pretty much has to be random, right, will preserve distances, will reduce the dimensionality and preserve distances with high probability for any subspace. Okay, so turns out the same essentially algorithmic strategy works very well here, in the sense that we can also construct a Gaussian embedding matrix, right? So Gaussian matrix is before matrix S, M by N matrix, and this will be an epsilon delta D oblivious subspace embedding, or OSE, for the embedding dimension, which is the dimension that we reduce down to, when M is big O of roughly D over epsilon squared, with some dependence on the failure probability delta, right? So it's of the order of D, which makes sense, and then we have to also pay for how accurate the embedding has to be. Okay, so these oblivious subspace embeddings have been studied for quite a while, and in fact have been one of the main tools, both theoretically and algorithmically, in using the so-called matrix sketching and developing algorithms for randomized linear algebra, right? So this, we're starting with some of the early works, such as Thomas Shalos's work. So that's that's been very successful, and it has led to fast algorithms and complexity improvements to tasks such as least squares regression, lower rank approximation, and as well as linear and nonlinear programming tasks. And so the basic idea here is, we use this randomized matrix S, like we defined earlier as a Gaussian matrix, for example, and we essentially use that to reduce the size of our input matrix for a matrix problem like least squares regression, right? And it turns out there's a natural way to associate a subspace with the corresponding input matrix A in such a way that a subspace embedding guarantees that the properties of the matrix will be well preserved by the small sketch that you end up with this embedding. Now, of course, things are not so simple here. If we try to use the simple Gaussian matrix that we mentioned in the previous slide, this will in fact result in quite expensive matrix multiplication steps. So we have to multiply this matrix S by the input matrix A. So this is expensive. We would like to avoid that to actually get some meaningful computational improvements. So along the way, one of the solutions for doing this that was proposed by Clarkson and Woodruff was to use a sparse matrix S. So the classical example of a sparse matrix S, which I will explain next, is a count sketch. So essentially the idea is if we can drastically sparsify the matrix S, the random matrix, then the application of the matrix multiplication will be much cheaper. So just to kind of give you an idea of what that looks like, we have a Gaussian sketching matrix on the left, right? So that effectively what it does is it takes any row vector of the input matrix A and sort of spreads it kind of across M different buckets of information that are stored in the sketch. And the idea of the count sketch is to instead pick a single bucket, right? So this is all described in the column of the sketching matrix S. So instead of spreading it along M buckets, we pick a single bucket. We use a little bit of randomness in this ±1 entry there, and kind of encode, or mix in this row of the matrix A there. And so we get a very, very sparse matrix S because it only has one non-zero entry per column. And so that leads to very fast algorithms. And that gives you a certain guarantee for subspace embedding, as we will talk now. But this has led to a flurry of works on looking at the sort of optimizing the trade-offs between how sparse a matrix, an embedding matrix, should be, and what sort of a guarantee we can get, right? So starting with, we have the Gaussian matrix, which is has a embedding dimension roughly of order d over epsilon squared, but it's completely dense, meaning that the number of non-zeros per column of this matrix S is m, as we've seen in the previous slide. On the other end of the spectrum, we have count sketch, which is essentially as sparse as could be, with one non-zero per column, but it has, it requires a substantially larger embedding dimension of the order of d squared, right, as opposed to d. And then a number of follow-up works, including Nelson and Nguyen, showed that if we increase the sparsity a little bit up to a polylog over epsilon per column, then we get closer to the optimal Gaussian embedding dimension, so d times polylog, and those logarithms have been later improved by in particular by Cohen. So that there has been quite a bit of progress on this, and there has been also a lower bound, which basically says, well, the embedding dimension obtained by Gaussians is essentially optimal up to a constant factor. And in fact, to achieve this embedding dimension, the lower bound says we should expect to need roughly log d over epsilon non-zeros per column. So clearly, the main gap in what's known right now, and this is kind of formulated in the conjecture that Nelson and Nguyen made, is how do we get to the actual optimal embedding dimension, which is this d over epsilon squared, using a sparse oblivious subspace embedding, right? And really, as you can see, this is unclear how to do with any non-trivial level of sparsity, right? Because the only embedding here that gets it is actually the Gaussian embedding, which is dense, right? So they conjecture that in fact the lower bound can essentially be matched, right? With roughly of the order of one over epsilon non-zeros per column, and then with the embedding dimension d over epsilon squared, as we mentioned. So the first main result of this work is basically to show that there is an OSE with optimal embedding dimension, as we've shown, d over epsilon squared, and non-trivial number of non-zeros per row, per column, specifically polynomial in log d over epsilon, right? So what's remarkable of this result? Well, it's really the first one to match the conjecture and lower bound on the embedding dimension that I mentioned earlier, under any non-trivial sparsity, right? But in fact, the sparsity we get here is pretty good for the most useful case of oblivious subspace embedding, which is when we want a constant distortion epsilon. So for constant epsilon, right, the sparsity here is polylogarithmic in d, so it's essentially nearly optimal. And in fact, the embedding dimension we can get here, there's no big constant factors hidden in the big O for the M, right? Really, we can get anything that's bigger than d, can achieve a subspace embedding property with this sparsity. I'll talk a little bit later about the analysis and some of the ideas from Gaussian universality that are crucial for this. So some of the applications here. So putting this together with several other oblivious subspace embedding results, we can actually turn this into a fast algorithm, which so this is stated in a kind of a common form for oblivious subspace embeddings as a sketch of a matrix A. And basically it says that essentially in input sparsity time, which is described here as NNZ of A, we can obtain this oblivious subspace embedding with optimal embedding dimension for an epsilon, for a constant distortion epsilon, right? So, and what's remarkable, this is the first optimal OSE faster than current matrix multiplication time, big O of d to the omega, right? Because the polynomial dependence on d here is essentially d squared. Okay, so and you can directly translate this into a kind of a nice result for least squares regression. So essentially showing how to do single pass least squares in optimal time and space. But I don't have time to go into more details on that. Now, our second main result, we ask the question, okay, so can the sparsity be further improved for subspace embeddings? And I mean beyond the conjecture of Nelson and Nguyen. And it turns out, well, if we allow non-oblivious embeddings, then the answer is yes. And specifically, and of course, here we also want to get this optimal embedding dimension. So this is kind of the core of all of our results, that they achieve the optimal embedding dimension. So what we want is so what we show basically is if we have some additional knowledge about our input, so the input matrix or the subspace basically, and in this case, the knowledge is some approximations of the leverage scores of this matrix. I'll mention leverage scores later on in a second, what they are. Then we can construct a subspace embedding for this particular subspace with optimal embedding dimension, where the matrix S has, again, there's this poly log D over epsilon non-zeros, but this time per row and not per column of the matrix, which in fact is a lot better. Per row means that actually the whole matrix is much sparser, as we will see in a second. So what's remarkable about this, so this uses a technique which was recently introduced called leverage score sparsification, which is closely related, as if you're familiar with leverage score sampling, right? It's closely related to leverage score sampling, but remarkably, leverage score sampling cannot achieve this result because there's no lower bounds that say, the coupon collector lower bound says that leverage score sampling by itself cannot achieve the optimal embedding dimension. So just to quickly explain leverage score sparsification. So leverage score sampling, we can view this as, essentially subsampling the rows of the matrix A according to importance probabilities, which are, defined in some way, in some natural way. So in terms of sketching, we can view this as, we're picking a single, so for each row of the sketching matrix S, we're picking a single row of the matrix A, and that's our sample. And leverage score sparsification is the idea of, okay, well, let's pick a couple rows of matrix A, several, but not too many, all of them sampled according to leverage scores, and put them in this one row of the sketching matrix S, right? So it's a little bit denser than leverage score sampling, but it's still much, much sparser than even potentially than count sketch, right? Because there's much fewer rows here than columns, right? So it's extremely sparse. And so again, with a little bit of extra work, including approximating the leverage scores and so forth, we can actually turn this into a fast, low distortion subspace embedding, no longer oblivious, which basically says, given a particular matrix A, we can compute a sketch SA, right, where S is the subspace embedding up to distortion epsilon, right, and we have the optimal embedding dimension of the order D over epsilon squared, and we have the runtime that is essentially input sparsity plus d to the omega, so the current matrix multiplication time. And again, this is the first low distortion subspace embedding to achieve that. And so naturally, we can again give a natural application for this, just based on standard applications of subspace embedding to solving a range of regression tasks. So this this can be placed in a context of other recent works aiming towards achieving optimal subspace embedding guarantees. So here's some of the comparison. I mean, essentially, the main difference between our work and those previous works is that we are actually focusing on sparse subspace embeddings, which has advantages for the tasks I mentioned, and we are also able to achieve for the first time low distortion embeddings in the optimal embedding dimension in essentially runtime that matches the runtime of the previous work on this. Okay, so as far as the analysis goes, I will just briefly mention one of the key tools we use is essentially Gaussian universality results for random matrices, for models of sums of IAD random matrices, which essentially, this is an example here from Brailovsky and Van Handel, which goes substantially beyond what has been used classically, such as the standard sort of matrix concentration results like matrix Bernstein or matrix Chernoff. So these approaches here, kind of directly compare the spectrum of a random matrix model to the spectrum of a Gaussian and the analogous Gaussian matrix with the same covariance structure, and they allow you to get much sharper guarantees. Okay, so in conclusion, the focus of this talk was essentially on addressing the following conjecture by Nelson and Nguyen from Fox 2013, which was claiming that there is an OSE with the optimal embedding dimension d over epsilon squared and log d over epsilon non-zeros per column. We are able to show this optimal embedding dimension with poly of log d over epsilon non-zeros per column, right? So the non-zeros per column is not quite there yet. We are also able to obtain a fast algorithm out of this, which is based on levered score sparsified embeddings, less embeddings, which achieves this optimal embedding dimension even with a epsilon that can be polynomially small in D, and still in time that's essentially input sparsity plus matrix multiplication time. So the natural follow-up question is, can we close the sparsity gap for optimal OSEs, right? So we've actually since made some progress on this, and our ongoing work have been able to show that you can achieve, have been able to get the right dependence on epsilon in the sparsity, but not yet on the polylogarithmic factors. Okay, that's our paper, and thank you for your attention.